Imagine standing in the middle of a bustling city,
Yeah.
and you're trying to catch this really crucial message, but it's just a whisper, maybe only a few feet away.
Right. Against all that background roar.
Exactly. That's often the kind of challenge engineers face. They're trying to isolate a really faint signal amidst this uh, constant, unavoidable background hum of modern electronics.
It's everywhere.
Every single circuit, every connection, even just the air around us, it adds its own little rumble to this, this noise floor. But what if we could actually quantify that rumble, measure it precisely?
And maybe even pick the quiet parts.
Yeah. What if we could measure exactly how much unwanted noise a device contributes and then, choose components that perform like a silent library instead of a roaring rock concert?
That's the goal, isn't it?
It is. So today we're taking a deep dive into the fascinating and often, let's be honest, intricate world of noise factor measurement.
And specifically using a spectrum analyzer for that.
Right. We're going to explore how engineers use that tool to assess exactly how much additional unwanted noise an electronic device injects into a signal.
Okay.
Our mission today is pretty clear. We want to equip you, our listener, with a really crystal clear understanding of what noise factor actually is, why measuring it accurately is just so critical for performance.
And the different ways to do it, I imagine, the method.
Exactly. The various methods along with their, clever tricks, those hidden pitfalls we always seem to find, and sometimes surprising advantages that engineers use to tackle this challenge in the real world.
Sounds good. And we're drawing on some source material.
We are. We'll be pulling insights from a really detailed article called Ali Pradelio, AHS, Elia Cosa, Caveta.
Yeah.
It's by ymikhail and Habr, published back in May 2024.
Habr. Good stuff often comes from there.
It does. And, whether you're a seasoned RF engineer listening in or maybe a student just eager to peek behind the curtain of wireless communication, or honestly, just someone who appreciates the hidden complexities that underpin the devices powering our digital lives. Understanding noise factor is really key.
It impacts so much.
Totally. Everything from the range and reliability of your Wi-Fi to the clarity of deep space satellite communications, the speed of data transmission, and just the overall efficiency of countless electronic systems.
Yeah, getting this right means better tech, basically.
Better, more reliable technology, often without needing to just, bulk up on power consumption or resort to these massive, impractical antennas. Okay, let's unpack this. Let's tune into the subtle art of noise detection. So let's start right at the beginning, the absolute fundamentals. What exactly is noise factor, and why does this concept, which might sound a little abstract at first, hold such immense practical importance in the very real world of electronic design?
It's a great place to start because the core idea, it's actually quite intuitive once you get your head around it. Noise factor, or MA, and you'll also hear it called noise figure, or NF, especially in, English-speaking contexts. It's a really critical metric in analog electronics.
Okay.
Think of it maybe like a quality rating for how cleanly a device processes a signal. At its heart, it measures how much an analog path degrades the signal-to-noise ratio, the SNR, of a signal as it passes through.
Okay, so it's about degradation.
Exactly. If you send a pretty clean signal, maybe with some noise that's already there, into a device, the noise factor tells you how much extra noise that device itself adds on to your signal.
That's a really helpful way to think about it. So if a device has a small noise factor, that means it's a cleaner amplifier. It's adding less of its own unwanted noise. That makes sense.
Precisely. A smaller means the device is, let's say, more transparent. It adds less of its own internal clutter, its own hiss. And this has a direct and often incredibly significant practical impact.
Like what, for instance?
Well, devices with a low AWI can dramatically increase the effective data transmission range or speed in a communication channel. Think about it. If you're trying to communicate over a huge distance, right? If your receiver adds very little noise of its own, it can pick up much, much fainter signals before they just get completely swamped by its own internal noise.
Okay, so sensitivity improves.
Right, which means you don't necessarily have to pump in more energy at the transmitter or use bigger, more expensive antennas to get the same performance. It's an efficiency gain.
Efficiency, that's key.
It really is. It translates directly into better performance, often smaller devices, and frequently lower power consumption. This is where it gets really interesting because it's about making systems work smarter, not just, harder or bigger.
So it's not just about how much a signal gets amplified, but how much purity it keeps during that process. It's a really crucial distinction.
It is.
But, okay, to quantify this purity, this noise addition, I understand there are a few standard ways to actually define numerically. Can you walk us through those different perspectives?
You're right, yeah. There are a couple of main ways to look at it, each giving a slightly different angle on quantifying this noise degradation. The most fundamental one, the sort of classical definition, looks at the ratio of signal-to-noise ratios.
Okay.
It basically says that, let's call it F when we're talking linear terms, not dB, is the ratio of the signal-to-noise ratio at the input of a device.
SNR in.
Right, SNRIN, divided by the signal-to-noise ratio at its output, SNROut.
Okay, so sin and in divided by sout now.
Exactly. S is signal power, N is noise power, in and out. This definition directly captures how much the device itself messes up the quality of your signal compared to the noise. If your output SNR is way worse than your input SNR, F is going to be high. Shows a noisy device. It's a measure of that relative degradation.
Relative degradation. What's the other perspective?
Then we have a more, let's say, standardized definition. This is really useful for comparing different devices fairly, like the Russian standard JOE S2437580, and many international standards do something similar. They define with a specific reference temperature in mind, usually 293 Kelvin for ghost.
Why the specific temperature?
Because noise is related to temperature, right? Thermal noise. So fixing the temperature gives you a stable baseline. According to GOC is the ratio of the actual noise coming out of the device
No.
to the output noise it would produce if it were a perfect, ideal, totally noise-free amplifier.
The ideal case.
Exactly. An ideal amplifier that's just amplifying the input thermal noise, the noise from a resistor at that standard reference temperature with the same gain.
Okay, so it's like comparing the real device to a perfect one.
Precisely. The formula looks like F equals note, G in thermal 293K. Nout is the real output noise, G is the device's gain, and in thermal 293K is that theoretical input thermal noise at 293 Kelvin, calculated over whatever bandwidth you're using.
Okay.
This way is powerful because it isolates the device's own noise contribution by comparing it to that theoretical perfect amplifier. It directly tells you about the extra noise the device adds, makes it a great benchmark.
So one looks at the practical drop in SNR, the other compares to this ideal, perfectly quiet amplifier at a fixed temperature. The key thing, it seems, is that both are trying to give engineers a common, objective way to talk about noise.
That's the idea.
And the GOST standard, by fixing that input temperature, lets you compare devices properly, right? Like apples to apples, regardless of maybe the lab temperature that day.
Exactly. It gives you that highly repeatable benchmark, crucial when you're looking at device specs.
I'm guessing, in practice, we usually talk about this in decibels, dB, not these linear F values.
Oh, absolutely. Yeah. For practical convenience, and because we're often dealing with huge ratios between signal and noise, is almost always expressed in decibels. Just easier numbers. Much easier. The conversion is simple. NF equals 10 log F. This logarithmic scale just makes those big ratios more manageable and fits right in with how engineers usually think about and measure power levels in RF and communication systems. It simplifies things for day-to-day work.
Okay, so we've nailed down what noise factor is and why it's so important. But measuring it accurately, that sounds like it needs extreme precision. And you need to understand a lot of subtle factors, right?
Mm-hmm.
What are some of the particular quirks and challenges engineers run into when they're trying to get a really accurate reading of F of N?
Yeah, this is where our deep dive really starts to get granular because the little details in the measurement can totally change your results. One absolutely critical thing is the temperature of the noise source.
We just touched on that with the GOST standard.
Exactly. F, as we just said, is fundamentally defined at a fixed standard noise source temperature. Why? Because that temperature directly sets the input thermal noise power. The formula is N, annual KTB.
KTB noise.
Right. K is Boltzmann's constant, that fundamental link between temperature and energy. T is the absolute temperature in Kelvin, and B is the bandwidth you're measuring over.
So if my lab is warmer or colder than the standard,
your input noise level changes. And if your input noise baseline is different from the standard the definition assumes, your measured may will be off. It's that simple.
So even just a few degrees difference between my lab bench and the standard 290K or 293K could actually throw off a measurement. That feels surprisingly sensitive.
It absolutely can be, especially when you're chasing really low noise figures. So standards bodies specify these temperatures for consistency, i.e. OOT often uses 290 Kelvin. JST 2437580 uses 293 Kelvin. But in the real world, like in the measurements in our source article, the lab temperature was around 24 degrees Celsius.
What is 1 Kelvin?
That's about 297.15 Kelvin, so a few degrees warmer than the standards. These subtle differences matter.
Okay, so how do engineers deal with that? Do they heat or cool their labs?
Not usually. Well, sometimes for calibration labs, maybe. But more practically, they often use the concept of spectral power density, SPD.
Okay, SPD, what's that?
It's usually in watts per hertz, or more commonly, dBm per hertz. It lets you sort of abstract away the bandwidth and just talk about the noise intensity per unit of frequency. It makes things more universal.
Noise per slice of frequency.
Pretty much. Now, even with SPD, the exact theoretical noise floor value will shift slightly with temperature. For 290K, it's medical 173.975 dBm hertz. For 293K, it's medical 173.975 dBm hertz. For 293K, it's NETIC of 173.93 BMM hertz. It was MEDIC of 173.87 dBm hertz.
Tiny difference.
Yeah, like very small, yeah. Less than a tenth of a dBm. So the author of our source article made a practical call. That's a pretty common engineering trade-off, understand the error, decide if it's acceptable. The key thing is knowing which reference temperature is being used, or if a practical rounding like this has been applied.
Got it. So temperature is one dance partner you have to master. What about the connections themselves between devices? I've heard mismatch can be a real pain in RF work.
Oh, mismatch, yes.
Yeah.
It's a very significant factor, and it can definitely lead to unreliable, unstable results. When you have an impedance discrepancy, basically a mismatch between your noise source and the input of the device you're testing, the DUT.
Like trying to connect a 75 ohm cable to a 50 ohm input.
Kind of, yeah, or just subtle variations from the ideal 50 ohms. This mismatch causes reflections. Signals bounce back, and these reflections can interfere with the signal you're trying to measure, causing what the source calls pulsations. Basically, the reading jumps around.
Like trying to weigh something on a bouncy scale.
Exactly. Makes it hard to get a stable, repeatable reading. There's a neat practical trick to check if mismatch is messing with you.
Oh yeah, what's that?
You add a known length of transmission line, like a piece of precision airline cable, into the input path between the source and the DUT.
Okay, why?
Because adding that line changes the phase of any reflected signals. If you add the line and your measured SEB graph doesn't change much, then mismatch probably isn't a big issue for that specific DUT.
Oh, clever.
But, and this is crucial, you must account for the cable's own losses when you do this check. Otherwise, you're adding loss and thinking it's a mismatch effect.
Right. Got to subtract the cable loss itself.
If the graph does wiggle around significantly when you add the phase shifting line, that's a big red flag. It tells you the DUT is sensitive to impedance, and you might need better matching to get truly accurate, stable results. It's a smart diagnostic step.
It is a neat trick. Okay, phase shifting lines for mismatch checks. Now let's talk about the cables themselves. The everyday patch cords connecting everything. Seems basic, but I sense a trap.
Yeah.
Is there a cable conundrum here that trips people up?
You've absolutely hit on one of the most common and honestly critical pitfalls. The source really emphasizes this. You have to accurately account for losses in your measurement cables. But here's the specific rule. The correct procedure says you should only subtract losses from the input cable. That's the cable between your noise source or signal generator and the input of your DUT.
Why only the input cable?
Because any loss before the DUT effectively reduces both the signal and the noise power that actually reaches the DUT's input, so you need to factor that loss in to know what the DUT is truly seeing.
Makes sense. The DUT sees a weaker signal because of the input cable loss.
Right. Now, here's where it gets really interesting, and frankly, where a lot of measurements go wrong, often without anyone realizing it. A surprisingly common mistake is subtracting losses from the output cable as well, the cable between the DUT output and the spectrum analyzer.
Okay. Why is that wrong? Seems like you'd want to account for all losses.
It leads to an overly optimistic result. It makes your DUT look better, quieter than it actually is. It gives you a misleadingly low value.
Whoa, okay, why? Explain that.
Okay, think about how noise adds up in a chain. There's a formula, the cascaded elements formula, sometimes called Fries's formula, for total F1 plus, F21, G1 plus, F31, G1, G2 plus, and so on.
All right, F1 is the first stage's noise factor. G1 is its gain.
Exactly. F2 is the second stage's NF, and its contribution is divided by the gain of the first stage, G1. The noise of later stages matters less if the early stages have high gain. Now, think about a passive device, like a cable. Its noise factor, in linear terms, is basically equal to its loss, or you could say its gain is less than 1.
Okay, so a cable has an NF equal to its loss.
Right. So if you put that output cable after the DUT, its noise contribution is already baked into the total noise power you measure at the output. It's part of that F total. Its individual NF contribution is buried in those later terms of the Friese formula. It becomes something like F cable 1 divided by the total gain of everything before it, G1, G2.
Ah, so it's not a simple subtraction.
Definitely not. Just subtracting the output cable loss directly from your final measure is mathematically wrong. It overcompensates, effectively removing noise that was genuinely there, giving you that artificially low, rosy number.
Yeah.
The author specifically mentions seeing this error happen in practice and suggests it should be the first thing you check if someone reports a receiver, a value that seems suspiciously good.
That's a massive aha moment.
Yeah.
Input cable loss.
Yeah.
Yes. Subtract it. Output cable loss. No, don't subtract it directly. It's already accounted for in the output noise measurement.
That feels like a lesson learned the hard way for many.
I suspect so. It's subtle but profound. Get it wrong, and you could choose a worse component based on faulty data. Critical takeaway. Only subtract input cable loss.
Okay, crucial point hammered home. What about mixers? They're often key components in RF systems doing frequency conversion. Do they have their own special noise factor mysteries?
They absolutely do. And this is another area where the standard advice can sometimes lead you astray if you're not careful. We know the rule. In a cascaded system, the overall noise factor is dominated by the first stages.
Right. Put a good low noise amplifier right at the front with high gain. That's the usual strategy. That's the standard playbook, yes. Amplify the signal cleanly before it hits potentially noisier downstream components. But, and this is a really critical nuance, the source points out this assumption holds true only if your frequency converter, your mixer, is designed correctly.
What could go wrong with the mixer design?
Here's the hidden trap: image channel noise. Mixers, by their nature, can take signals from two different input frequency bands and convert them down to the same output frequency, the intermediate frequency, or IF. One is your desired signal channel. The other is the unwanted image channel. It's like a mirror frequency on the other side of the mixer's local oscillator, LO frequency.
Okay, I remember image frequencies. They're usually filtered out, right?
Ideally, yes.
Yeah.
But if the filtering before the mixer isn't good enough, or if the mixer itself doesn't have good image rejection, significant noise from that unwanted image channel can leak into the mixer input right along with your desired signal's noise.
And what does that do?
It effectively doubles the total noise power that the mixer has to deal with right at its input stage. And if you double the input noise power, guess what happens to your overall system noise factor?
Uh-oh. It gets worse.
It gets at least 3 dB worse.
Yeah.
Instantly, regardless of how amazing and low noise your input LNA is.
Wow, 3 dB. That's a huge penalty.
It is. It's like trying to listen to your favorite radio station, but another station broadcasting pure static at the exact same volume is somehow getting mixed in. It just degrades everything significantly.
So you could spend a fortune on the best LNA. But if your mixer lets in image noise, you've basically shot yourself in the foot.
Precisely. The source makes this point very clearly. If you find yourself improving your LNA, getting lower NF, higher gain, but your overall receiver just isn't getting any better, stop looking at the LNA. It's time to scrutinize your frequency converter's architecture.
Are we chasing the wrong culprit?
That's the exact question the article implies you should ask. The problem might not be the amplifier. It might be the mixer's inability to reject that unwanted image noise. It's a powerful reminder that you have to think about the whole system, how components interact, especially with mixers. Those hidden paths for noise can really bite you.
Okay, we've just navigated a real minefield, haven't we? Temperature quirks, mismatch mayhem, the critical cable conundrum, and these sneaky mixer mysteries. It's crystal clear that getting an accurate noise factor measurement is far from simple.
Definitely requires care.
So having understood what can trip you up, let's shift focus to how engineers actually set up these measurements, specifically using a spectrum analyzer. How do they tackle these challenges and aim for reliable results? Can you give us an overview of the typical measurement process outlined in the article?
Certainly. The article uses a practical case study, which is really helpful. They measure a low-noise amplifier, an AGA, designed for the 24 to 33 gigahertz band. Quite high frequencies.
Yeah, millimeter wave territory almost.
Right. This specific device had a WR28 waveguide input, that's rectangular metal pipe for signals, and a standard 2.92 millimeter coaxial connector output.
Okay, waveguide in, coax out. How do they connect that to coax test gear?
Good question. They used a coaxial to waveguide transition, and they made a practical decision here. They treated that transition piece as part of the device under test, the DUT.
Ah, so its losses just get included in the overall measured performance.
Exactly. It simplifies the setup because you don't need to separately characterize the transition's loss and subtract it out. It's a common approach when the transition is always used with the device anyway.
Okay, so what's the overall process?
The whole process of measuring us with a spectrum analyzer is broken down into 4 main stages in the article. A nice, clear roadmap. 1. First, you need to get a handle on the DUT's gain. How much does it amplify? 2. Then, crucially, you have to estimate the spectrum analyzer's own noise factor. Your measurement tool adds noise too. 3. Then you assemble the whole setup and actually measure the noise level coming out of the DUT's output. And 4, finally, you take all that data and calculate the noise factor.
Okay, 4 clear steps. Gain, SA noise, DUT output noise, then calculate. Let's take step 1, estimating the DUT's gain. How do you accurately figure out how much amplification the DUT provides?
Right, the gain or its amplitude frequency characteristic across the band. The gold standard, if you have it, is using a vector network analyzer, a VNA. The article mentions using a Keysight N5244B, for instance. VNAs are designed for precise gain and phase measurements.
But not every lab has a high-frequency VNA. What's the alternative?
The alternative, and very common, is to use a signal generator and your spectrum analyzer. The basic idea is connect the generator to the DUT input, connect the DUT output to the spectrum analyzer, SA.
Okay.
Then you sweep the generator frequency across the band you care about. At each frequency, you note the generator's output power, and you measure the power coming out of the DUT on the SA. The difference is the gain. Output power minus input power in dB.
Simple enough. Any tricks to make that more accurate?
Yes, a key tip from the source. To minimize errors, it's highly recommended you measure the generator's output power directly with the same spectrum analyzer you're using for the output measurement. Don't just trust the number on the generator's display.
Why is that?
Because the SA's relative power measurement accuracy, how well it measures a change in power, or the difference between 2 power levels, is often much better than its absolute accuracy, how well it measures a specific dBm value against a true standard. By using the SA for both input from the generator and output from the DUT, you reduce the impact of any absolute calibration error in the SA.
That makes perfect sense. Use the same ruler for both measurements.
Exactly. Now, there's an interesting point for one of the methods we'll discuss later, the power doubling method. For that specific method, you actually only need an approximate gain measurement.
Oh. Why only approximate?
As long as you can confirm that the DUT's gain is high enough specifically, at least 15 dRds higher than the spectrum analyzer's own AMA, that's sufficient for the method to work well. We'll get into why later, but it relaxes the gain measurement requirement a bit in that case.
Okay, good to know. So that's gain. Now, step 2, calibrating our own tool, estimating the spectrum analyzer's own noise factor. This feels critical, like measuring the noise of your microphone before you record something quiet.
It is absolutely critical. If your measurement tool is noisy, how can you accurately measure the noise of something else? You need to know the baseline noise floor of your instrument. The article used a CYDEA 4051H spectrum analyzer, and they outlined 2 main ways to estimate its NF, which provides a really valuable cross-check.
Okay, 2 methods. What's the first one?
Method 1. Direct measurement using the noise marker, SPD function. This uses the SA's built-in capability. For the setup, you connect a good quality 50 ohm matched load directly to the SA's input. This load acts like a perfect, quiet noise source at whatever the ambient lab temperature is.
Got terminated input.
Then you configure the SA for maximum sensitivity. This usually means spectrum mode, swept SA analysis type, set your center frequency. They use 28 gigahertz. A reasonable span, like 100 megahertz. Choose appropriate resolution bandwidth, RBW, and video bandwidth, VBW settings. They used 500 kilohertz RBW and 1 kilohertz VBW, which are common for noise. Definitely turn the internal preamplifier on, and set any mechanical attenuation to 0 dB. You want the clearest possible view of the noise floor.
Max sensitivity settings, got it.
Once it's set up, you place a marker right at your frequency of interest, 28 gigahertz in the example, and you activate the SA's noise marker function. This function is specifically designed to measure and display spectral power density, SPD, directly, usually in dBm hertz.
That SPD value again.
Yep. The SA in the article measured Mugganish 161 dBm hertz at 28 gigahertz using this method. Now, to get the noise factor of the SA itself, you just subtract that theoretical input thermal noise density we talked about earlier.
The negative 164 dBm hertz value.
Exactly, the rounded value they used. So NFSA equals PSDSA measured PSDN. That's negative 161 dBm hertz minus negative 174 dBm hertz, which equals 13 dBm.
Okay, 13 dB noise factor for the SA using the direct marker method. What's the second method?
Method 2, the power doubling method with channel power for cross-check. This is clever. It's great for checking if the SA's direct measurement and internal calibration are trustworthy. It relies more on the accuracy of your signal generator.
Okay, using the generator to check the SA. How does that work?
Setup. Connect a good high-frequency generator to the SA input. Initially, set the generator to a very low power, like -100 dBm, and make sure modulation is OFF and the RF output is also OFF.
Generator connected but off.
Right. Now, configure the SA for channel power measurement. This mode measures the total power within a specified bandwidth. Settings would be something like spectrum mode, Mies channel power function, preamp on, ATN 0 dB, maybe a span of 50 MHz, and crucially, an integration bandwidth, Integ BW. They chose 25 MHz.
Why 25 megahertz?
It's a compromise. Small enough that the SA's own noise figure hopefully doesn't change wildly across that band, but wide enough that the total noise power in that band is significantly above the minimum power level your generator can accurately produce. You also set your center frequency, 28 GHz, RBW 500 kHz, and VBW 1 kHz.
Okay, SA set for channel power over 25 megahertz. What's the procedure?
It's elegant. Step 1. With the generator still OFF, measure the channel power. This reading represents the SA's own internal noise power integrated over that 25 MHz bandwidth. In the article's example, this was an NME 6.9 dBm.
Got it. SA's noise floor power.
Step 2. Now turn the generator on. Carefully, slowly, increase the generator's output power level until the channel power reading on the SA increases by exactly 3 dB from the baseline you just measured.
Ah, the 3 dB jump.
Exactly. So if the baseline was NH 86.9 dBm, you adjust the generator until the SA reads precisely an NH 83.9 dBm, or they got an NH 83.82 dBm in their measurement. That exact 3 dBm increase tells you something very specific.
What does it tell you?
It tells you that the power being delivered by the generator is now exactly equal to the SA's internal noise power within that 25 MHz band. Adding equal power doubles the total power, which is a 3 dB increase.
Clever. So the generator setting at that point equals the SA's noise power.
Precisely. Well, equals the noise power referred to the SA input after accounting for cable loss. So now you calculate the SA's noise factor using a slightly different formula. NFSA is the PGen bum, IL cable B, PSD, BMR, 10 log BHz.
Okay, break that down.
PN is the generator power setting that gave you the 3 dB jump, -83.82 dBm in the example. IL cable is the loss in the cable connecting the generator to the SA, 2.27 dB. PS10 is our old friend, -174 dBm. And B is the integration bandwidth in hertz, 25b6 hertz.
And what did that calculate out to?
Plugging in the numbers from the article, they got 14.75 dB.
Okay, so method 1 gave 13 dB, and method 2 gave 14.75 dB. Those are pretty close.
They are quite close, yeah. Less than 2 dB difference. That gives you a good level of confidence.
What does that closeness imply?
It strongly suggests that the spectrum analyzer is functioning reasonably well and its internal calibration for the noise marker isn't wildly off. If the numbers were drastically different, say 10 dBs apart, you'd be very suspicious.
And which result would you trust more if they were different?
Generally, if you trust the absolute accuracy of your signal generator more than the SA's absolute calibration, the power doubling method, method 2, might be considered more reliable. It relies fundamentally on the relative accuracy of the SA, detecting that 3 dB jump, and the absolute accuracy of the generator.
That's fascinating. It's like having a built-in way to double-check your tools before you even start the main measurement on your actual device.
Exactly. It's about building confidence in your instrumentation. Know your tools before you trust their readings for critical design decisions. It's really smart metrology.
All right, our instruments are checked out, we know their noise contribution, and we've navigated those potential measurement quirks. Now, let's get to the main event. Measuring our actual device under test, the DUT. The article highlights this power doubling method as being practical and robust. You just used it to check the SA itself, so what's the core principle when applying it to the DUT, and what setup does it need?
Yeah, the principle is exactly the same as when we used it on the SA, just applied to the DUT now. It hinges on that elegant idea. If you inject a signal whose power is exactly equal to the noise power already present at the DUT's input within a specific bandwidth, the total power measured after the DUT will double.
Which means a 3 dB increase on the spectrum analyzer connected to the DUT output.
Precisely. So the moment you adjust your input signal generator just enough to cause that precise 3 dB jump on the SA measuring the DUT's output, you know that the generator's output power, minus input cable loss of course, is exactly equal to the DUT's equivalent input noise power over that measurement bandwidth. It's a really neat way to infer the input noise power.
Okay.
Yes, absolutely critical. For this method to give you an accurate measurement of the DUT's noise factor, the spectrum analyzer's own noise must be insignificant compared to the noise coming from the DUT after it's been amplified by the DUT's gain.
So the DET's output noise needs to dominate the SA's noise floor.
Right. The rule of thumb given in the source is NFDU-TDB plus GDU-TDB must be greater than NFSADD. The combined noise factor and gain of the DUT needs to push the noise level well above the SA's own noise floor.
Okay, NFDET plus GDUT NFSA, that's the baseline. And you also mentioned a 15 dB margin for really low error. Why that specific number?
Yeah, the 15 dB margin is for achieving high accuracy, specifically getting the methodological error below about 0.14 dB. The requirement is that the DUT's gain, or the total gain of your DUT, plus any needed booster amplifiers, should be at least 15 dBs higher than the SA's noise factor. So the condition becomes G total NFSA plus 15 dB.
Why 15 dB? What does that ensure?
It ensures that the noise power contributed by the SA itself is truly negligible, less than a tiny fraction compared to the amplified noise coming from the DUT. If the DUT's amplified noise is only slightly above the SA's noise floor, the SA's noise will still contribute significantly to the total measured power, corrupting your reading and making the DUT seem noisier than it actually is. That 15 dB separation pushes the SA noise down into insignificance for the measurement.
Got it. So that 15 dB is key for accuracy. Let's look at the article's example again. The single OH amplifier had about 21 dB gain, and the SA's NF was around 14 dB. Does that meet the condition?
Let's check. We need GNFSA plus 15 dB. So we need gain 14 dB plus 15 dB equals 29 dB.
Ah, and the DET only had 21 dB gain, so no, it doesn't meet the high accuracy condition.
Correct. A single 1K wasn't enough. So what was the clever solution they used?
They cascaded two of them, put two identical in dB.
Exactly. By connecting two identical amplifiers in cascade, they acted as a single DUT for the measurement. The total gain becomes roughly 21 dB plus 21D equals 42 dB.
And 42 dB is definitely greater than the required 29 dB.
Comfortably exceeds it. This ensures the measurement accuracy stays within that desired low error bound. And remember, because of how cascaded noise works, Freese formula again, the noise factor you measure for this two-stage DUT will effectively be the noise factor of the first OI in the chain. The second one's noise contribution gets suppressed by the gain of the first.
So doubling up lets you accurately measure one. That's really smart.
It's a very practical engineering solution. So the final setup for the measurement becomes test generator DUT, which is the pair of cascaded MSHUs, septus spectrum analyzer.
Okay, setup is clear. Now walk us through the step-by-step measurement procedure itself. How do we actually do it on the bench?
All right, let's break it down methodically. 1. Generator setup. First, set your signal generator to the frequency you want to measure, say 28 GHz. Dial its output power way down, maybe 100 dBm or so. Make sure modulation is O off F. And critically, start with the RF output O off F.
Okay, generator ready but silent.
2. Spectrum analyzer setup. Configure the SA for maximum sensitivity and channel power measurement mode. So, spectrum mode, Mies channel power function, select that integration bandwidth, they use 25 megahertz again. Preamp on, attenuation 0 dB, set your span, 50 megahertz, center frequency 28 gigahertz, RBW 500 kilohertz, VBW 1 kilohertz. Basically settings very similar to when we measured the SA's noise.
SA ready to measure power in that 25 megahertz window.
3. The measurement dance, finding the 3 dB point. Step A, baseline noise. With the generator still OFF, measure and carefully record the noise power shown by the SA in that 25 MHz channel power window. This is the total noise coming out of your DUT, the cascaded pair, plus any tiny residual SA noise. In the source example for the pair at 28 GHz, its baseline was around negative 58.7 dBm.
Record the noise floor power. Got it.
Step B. Double the power. Now turn the generator's RF output on then. Slowly, carefully increase the generator's output power level. Watch the channel power reading on the SA. Keep increasing the generator power until the SA reading is exactly 3 low dBAs higher than the baseline noise power you just recorded.
So if baseline was MEDIC 58.7 dBm, adjust the generator until the SA reads exactly NEDIFIC 55.7 dBm.
Precisely. You need to hit that 3 dB increase right on the nose. You'll see the noise floor visually lift on the SA display as you increase the generator power, and you stop right at that 3 dB mark.
Okay, stopped at the 3 dB point. What now?
Step C. Record generator power. At that exact point where the SA shows the 3 dB increase, immediately look at your signal generator and record its output power setting. That generator power level, after accounting for cable loss, is now known to be equal to the equivalent input noise power of your DUT over the 25 MHz bandwidth. For the 28 gigahertz example in the article, the generator power reading at the 3 dB point was a negative 95.3 dBm.
Record that critical generator power.
Step D, repeat for other frequencies. To get the noise factor across the whole band, you just repeat this whole dance, steps A, B, and C for each frequency you're interested in. You just change the center frequency on both the generator and the SA and do it again.
That's incredibly clear. It really is a methodical dance between the generator output and the SA reading. So once we've done this dance for all our frequencies and have that list of generator power values, PGen, how do we do the final calculation to get the actual noise factor?
The final calculation is pretty straightforward now that you have the key piece. PGen, the formula is NF equals PGen IL cabled B, PS done BM hertz, 10 log B.
Okay, same formula as before when we measured the SA, but now PGen is the value for the DUT. Let's break it down again.
Sure, PGen is that generator power setting that caused the 3 dB jump. It's our measured equivalent of the DUT's input noise power over bandwidth B. IL cabled B is the loss, in dB, of the input cable, only the one between the generator and the DUT input.
You get this right.
Input cable loss. Check. PS10B hertz is our assumed input thermal noise spectral density, that negation 174 dBm hertz value we've been using. And 10 log B hertz converts our integration bandwidth B, which was 25 megahertz or 25 D6 hertz, into its decibel equivalent so we can subtract it correctly.
Okay. Can you give us a couple of the results from the article's Table 1 using this formula?
Sure. Let's look at a few frequencies. At 25 gigahertz, the recorded PGen was 95.5 dBs. The measured input cable loss at that frequency was minus 2.17 dB. Plugging those into the formula gives a calculated noise factor, NF, of 2.35 dB.
Okay, 2.35 dBs at 25 gigahertz.
At 28 gigahertz, PDO was 95.3 dBs, and the input cable loss was 2.4 dBs. The calculation yields NF equals 2.45 dB.
Slightly higher. Makes sense.
At the 30 gigahertz, PDIN was 94.4 dBr, cable loss was 2.4 dBr, calculated NF comes out as 3.22 dBm.
So it's creeping up at the higher end.
Exactly. And plotting all these calculated NF values versus frequency gives you that nice graph, like figure 10 in the source, showing the incorrect on this power doubling method. What are the inherent trade-offs? What are its main plus points and its main drawbacks that an engineer needs to weigh up? Right. Every method has its pros and cons. Let's start with the disadvantages of power doubling. First, it really depends on the accuracy of your signal generator's output power setting. If the generator's absolute power isn't accurate, that error flows directly into your NF calculation. You're trusting that generator's dBm reading at that crucial 3 dB point. So
generator accuracy is key.
It is. Second, a practical issue. If your generator's minimum output power is relatively high, maybe it can't go down to an NX100 dBm reliably, you might have to use a larger integration bandwidth on the spectrum analyzer.
Why?
To make sure the total noise power within that bandwidth is high enough to be above the generator's minimum power, allowing you to find that 3 dB point. But using a very wide bandwidth can potentially mask sharp variations in the DUT's noise factor. You might average out peaks or dips that occur over a narrower frequency range. It's a trade-off. Sensitivity versus spectral resolution.
Okay, those are the cons.
Yeah.
What about the advantages? Why is it considered robust?
The advantages are pretty compelling, which is why it's used a lot. Maybe the biggest plus is that it's largely independent of the spectrum analyzer's absolute power measurement accuracy. It mainly relies on the SA's relative accuracy, its ability to precisely spot that 3 dB change. And relative accuracy is often much better and more stable than absolute calibration on many SAs. That's a huge benefit.
Bypasses the SA's absolute calibration issues.
Nice. Second, as we touched on, you don't need a super precise measurement of the DUT's gain beforehand. An approximate gain is usually good enough just to verify. You meet that G NFSA plus 15 dB condition to keep the SA noise negligible. Saves time and effort compared to needing pinpoint gain accuracy.
Less critical gain measurement. Good.
And third, a really important one. This method is capable of measuring devices with a high noise factor. Think about things like frequency converters, power amplifiers, sometimes even whole receiver front ends. These can have NFs of 10 dB, 20 dB, or even more. Other methods might struggle or fail entirely with such high noise levels, but power doubling often handles them just fine. Its versatility is a major strength.
Okay, the power doubling method sounds pretty solid, especially that independence from the SA's absolute accuracy. Now let's switch gears to the other main approach discussed. The direct method, sometimes called the cold source method. The name direct suggests simplicity, maybe. But given everything we've discussed about precision, I'm guessing there are some hidden catches here, too.
You are very perceptive. Yes, the direct method is conceptually straightforward. It really just applies the fundamental definition of FETI we talked about right at the beginning, the one based on the CGOS-T standard, but it's rewritten to use practical measurement units like dBm and dB, and specifically spectral power density.
Okay, what's the formula look like in this practical form?
The core formula they use is NFdB PSDOT BM Hertz, PSDM BM Hertz GdB.
Let's unpack that.
PSDOT is the noise spectral density you measure directly at the DUT's output in dBm Hertz. PSDIN is that theoretical input thermal noise spectral density, our Naker 174 dBm Hertz reference. And G is the DUT's gain, measured accurately and expressed in dB.
So measure output noise density, subtract the theoretical input noise density, subtract the gain.
That's the essence of it. The idea is simple. You measure the noise density coming out of the DUT when its input is seeing a known, quiet source, typically a matched load at ambient temperature, the cold source. You subtract the known input noise density, you subtract the gain the DUT added. And what's left should be the noise the DUT itself added its noise factor. It's a direct calculation based on the definition.
It does sound simple on paper, but I'm immediately thinking,
Right.
accurately measuring that gain, G must be absolutely critical here, right?
Right.
Much more so than for power doubling.
You've hit the nail on the head, absolutely. For the direct method, the accuracy of your DUT gain measurement, G, is paramount. You need to measure it precisely, whether using a VNA or very carefully using the generator and SA method we discussed. Any error in that gain value, G, will directly translate dB for dB into an error in your final calculated noise factor. There's no escaping it.
Okay, so precise gain is non-negotiable. What about the condition regarding the SA's noise floor? Does that still apply?
Yes, it does. Just like with power doubling, you still need to ensure that the amplified noise coming out of your DUT is significantly higher than the SA's own noise floor. That rule, G total NFSA plus 15 dB, still holds if you want high accuracy. The total gain of your DUT, plus any necessary auxiliary amplifier, needs to be at least 15 dBs greater than the SA's noise figure.
So you often still need that extra amplifier stage, even with this method.
Very often, yes, especially if the DUT itself doesn't have extremely high gain. The good news, again, is that if your DUT is the dominant first stage, low noise, high gain, the noise contribution of a decent auxiliary amplifier placed after it is usually negligible, thanks to the freeze formula. It gets swamped by the DUT's amplified noise.
Okay, and the measurement setup, is it different from power doubling?
It can be slightly different. If you already know the DUT's gain accurately and trust it's stable, you could technically just connect a matched load, the cold source, to the DUT input and measure the output PSD. That's the simplest form, like figures 11 and 12 hint at.
But the article used a generator.
Yes, the article describes a setup very similar to the one used for power doubling, like figure 6, including the generator. But here, the generator plays a different role. Its main purpose isn't for the 3 dB power doubling step. It's used primarily to accurately measure the overall gain, G, of the entire measurement chain, DUT plus auxiliary amplifier if used.
So the generator is mainly for the gain measurement part in this method.
Exactly. Let's walk through the step-by-step example they gave for measuring at 28 GHz using this direct method with the generator for gain. 1. Generator for gain. Set the generator to a known stable output power, say negative 65 GHz at 28 GHz. Modulation O off F, but RF output will be on for the gain part, O off F for the noise part.
Okay, known input signal.
SA for SPD. Configure the SA for maximum sensitivity and SPD measurement. So spectrum mode, preamp on, atom 0 dB, span 50 MHz, center freak 28 GHz, RBW 500 kHz, VBW 1 kHz. Critically, place a marker at 28 GHz and enable the noise marker SPD function.
Ready to measure noise density.
3. Measure output noise, PSDOT. Now with the external generator's RF output OF, so the DUT input effectively sees a quiet load via the generator's output impedance, assuming it's well matched when off, or you could physically connect a load. Measure the SPD at the output of the DUT chain using the SA's noise marker. In the example, this PSDOT was measuring 132.8 dBm Hertz at 28 GHz.
Record the output noise density. Got it.
4. Measure gain, G. This is the crucial two-part step for accuracy. Turn the generator's RFON at negative 65 dBm. On the SA, disable the noise marker function and just measure the peak signal power at the output of the DUT chain. Let's say it reads negative 27.9 dBm at 28 GHz. Now for that self-calibration trick, Disconnect the cable from the DUT input and connect that same cable coming directly from the generator straight into the SA input.
Yeah.
Measure the generator's power directly with the SA. Maybe the SA reads a negative 67.554 dBm for the generator's output.
Using the SA to measure the generator's actual output again.
Yep. Now calculate the gain. G integral pout chain pewed do output measured by SA. So G equals 27.9 dBm, negative 67.54 dBm. That gives you the gain of the chain.
Okay, gain measured carefully.
5. Repeat. Do steps 3 and 4 for all the other frequencies you need, measuring both PS out, generator off, and gain generator on at each point.
It definitely sounds meticulous. Both the output noise and the gain need careful measurement at each frequency. What kind of results did this method yield for the assay?
Right, the calculation uses NF equals PS out BM Hertz, PS and BM Hertz GdB. Let's look at table 2 from the source for a few points. At 24 GHz, the measured PGen, direct SA reading, was negative 69.2 dBm. The DUT chain output power, POUT2D, was negative 28.46 dBm. The measured output noise density, SPDOUT, was negative 133.1 dBm Hertz. This resulted in a calculated gain of 40.74 dBm and a noise factor of just 0.16 dBm.
Wow, 0.16 dBm. That sounds incredibly low. Almost too good to be true.
It does seem very low, especially compared to the power doubling results. Let's keep going. At 28 GHz, PGen was negative 67.54 dBm, POUT-TDs was negative 27.9 dBm Hertz, and SPDOUT was negative 132.8 dBm Hertz. The calculated gain was 39.64 dBm, and the noise factor was negative 1.5 dBm. Calculated gain was 41.72 dBm. PGen was negative 67.7 dBm Hertz. Calculated gain was 41.72 dBm Hertz, and noise factor was 3.18 dBm.
And that 3.18 dBs is also quite close to the power doubling result at 30 GHz, which was 3.22 dB.
Interesting.
It seems to agree better at the higher frequencies, but was way off at the low end.
That's a key observation, and we'll definitely come back to it in the comparison. Figure 16 in the source shows this trend visually.
I'm really keen to see that comparison graph now. But first, were there any specific pitfalls or common mistakes highlighted for this direct method, beyond needing accurate gain?
Yes, there's one big one the source specifically warns against, which can really mess up your SPD measurement. It's the mistake of trying to calculate spectral power density manually from a standard power reading.
How would someone do that?
They might put a marker on the noise floor, read the power in dBm, which depends heavily on the RBW setting, and then try to get SPD by just subtracting 10 log RBW from that dBm value.
Why is that wrong?
Yeah.
Seems mathematically plausible.
It's wrong because it completely ignores the complex characteristics of the spectrum analyzer's internal detector. Is it RMS responding? Peak sample. And any post-detection filtering or averaging that the SA applies. These aren't simple linear operations. The SA's built-in noise marker, SPD function, is specifically designed to account for all these internal factors and give a properly calibrated noise density reading.
So trying to outsmart the SA's dedicated function is a bad idea here.
Definitely. Trust the instrument's dedicated noise marker function for SPD. Don't try to derive it manually with oversimplified assumptions. That's a recipe for significant error.
Good warning. Okay, so let's summarize the pros and cons of this direct method.
Sure. The disadvantages are quite significant and stem from its core dependencies. First, a strong dependence on the SA's absolute power measurement accuracy. Any calibration drift or error in the SA's absolute dBm readings directly impacts your NF result. This is probably its biggest weakness compared to power doubling. Second, it requires a very precise measurement of the device's gain. Gain errors translate directly into NF errors. Third, like power doubling, it still needs that sufficient gain margin, G NFSA plus 15 dB, to minimize the SA's own noise contribution for best accuracy.
Okay, those are serious dependencies. What about the advantages?
On the plus side, if the DUT's gain is already accurately known, maybe from a trusted VNA measurement, then you don't strictly need the generator for the noise measurement part. You can just use a matched load at the input, measure PS out, and calculate NF. That simplifies the noise measurement setup itself.
Streamlined if gain is known.
Okay. And like power doubling, it is generally capable of measuring devices with high hack, which is useful for components like mixers or power amps.
So, comparing the two, it feels like the direct method's conceptual simplicity hides a greater sensitivity to instrument calibration, wouldn't you say?
That's a perfect way to put it. While it looks straightforward, measure output, subtract input, subtract gain, its reliance on absolute SA accuracy and precise gain measurement introduces a different and potentially more problematic set of challenges compared to the power doubling method, which cleverly sidesteps absolute accuracy issues by focusing on that relative 3 dB change. It really highlights that the easiest looking path isn't always the most reliable without understanding your tools inside and out.
We've really dissected these two spectrum analyzer methods now, power doubling and the direct method. They both have their strengths, weaknesses, and specific requirements. But before we put them head-to-head for the final verdict, I know there's another technique often mentioned, sometimes called the gold standard for noise factor measurement, the Y-factor method. Can you just briefly explain that one and how it fits into this landscape of precision measurement?
Absolutely. It's important to acknowledge the Y-factor method because it is arguably the most common and widely accepted technique for measurement in the industry.
Why is it so popular?
Its main strength lies in its inherent ability to cancel out several sources of error. It's often independent of the exact gain of the DUT and, critically, can be made independent of the absolute power calibration of the measurement receiver, like the spectrum analyzer.
How does it achieve that?
It typically uses a specialized noise generator or noise source. This isn't a signal generator. It's a device specifically designed to output two distinct, well-characterized levels of broadband noise power, usually controlled electronically. There's a hot state when an internal noise diode is turned on, generating excess noise, and a cold state when the diode is off and it just outputs thermal noise at ambient temperature.
Okay, hot and cold noise states. Then what?
You connect this noise source to your DUT input. Then, using your receiver, like an SA or a dedicated noise figure meter, you measure the DUT's output noise power twice. Once with the noise source in the hot state, let's call the power FOT, and once in the cold state, P cold.
Measure output noise for both input conditions.
Right. The ratio of these two measured output powers, FOT, P cold, is called the Y factor. The Y just stands for the ratio.
Okay, why P cold? How does that give you noise factor?
The noise generator itself comes with a calibration value called its excess noise ratio, or ENR. This ENR value tells you precisely how much more noise power it outputs in the hot state compared to the cold state, usually expressed in dB. There's a standard formula that relates the measured Y factor, the known ENR of the noise source, and the DUT's noise factor. By measuring Y and knowing ENR, you can calculate the DUT's NF very accurately. Because you're using a ratio Y factor, the absolute gain of the DUT and the absolute calibration of the receiver tend to cancel out.
That ratio is the key to canceling errors. Makes sense why it's the gold standard, so why didn't the article focus on it?
Simply down to equipment availability for the author, especially in that high 24-33 gigahertz frequency range. They mentioned they didn't have access to a suitable calibrated noise generator covering that full band when they did the main comparison work.
A practical limitation.
Exactly. They did mention getting a brief chance later to try it using high-end gear, an Agilent PXA signal analyzer, N9030A, and a 346CK01 noise generator, but they caution that those results were from limited time and might have random errors, so they're mainly illustrative.
Okay. But what if your SA doesn't have the fancy built-in Y-factor measurement option? Can you still use the principle?
Yes, the source makes a good point there. Even without the automated function, you can perform a Y-factor measurement manually. You'd need the calibrated noise source, and you'd manually switch it between hot and cold. You'd carefully measure the DUT output noise level on your SA for each state, maybe using the channel power marker. Calculate the ratio Y, FOT P cold yourself, look up the ENR for your noise source at that frequency, and then plug the numbers into the Y-factor formula to get NF.
More work, but doable.
More labor-intensive, definitely needs careful reading and recording, but the fundamental principle is sound, and it's a viable approach if you have the noise source but not the automated analyzer. The robustness comes from the method itself.
Okay, good to know Y-factor is out there as the benchmark. Now, for the big comparison, how did the three methods, power doubling, direct, and the brief Y-factor results actually stack up when measuring the same amplifier in the article?
This is really the punchline of the practical work, and figure 18 in the source tells the story visually. It plots the measured values from all three methods across the frequency band.
And what's the main takeaway from that graph?
The most striking thing is how the direct measurement method results diverge significantly from the other two, especially at the lower frequencies, like 24-27 gigahertz.
How do they diverge? Higher? Lower?
Both, actually. In the graph, the direct method results sometimes appear much lower, sometimes higher, than the power doubling and Y-factor results in that lower frequency range. They seem less consistent. The power doubling method and the Y-factor method, however, show reasonably good agreement with each other across most of the band. They track much more closely.
So direct method is the outlier, particularly at lower frequencies. What's the author's explanation for that?
The author strongly suspects, and presents a good argument for it, that the discrepancy is likely due to issues with the spectrum analyzer's absolute power measurement accuracy.
The weakness we identified for the direct method.
Exactly. It comes back to bite here. The direct method relies heavily on that absolute PS doubt measurement being correct. The author makes an intuitive point. A signal generator, which is designed primarily to output a clean, single tone at a precise power level, might just be inherently simpler and thus more accurate in its absolute power output than a complex spectrum analyzer.
Why would the SA be less accurate?
Wow.
Absolutely.
An SA has a much more complicated job. Its analog front end has to handle a huge range of signal levels and frequencies, often involving multiple stages of mixing, filtering, amplification, and complex detection schemes. RMS, peak, sample, etc. Each of these stages can introduce small cumulative errors in the absolute power reading displayed. However, its ability to measure a change in power, relative accuracy needed for the 3 dB jump in power doubling, is often much more stable and reliable.
That makes a lot of sense. Simpler instrument generator might be better at absolute levels. Complex instrument SA might be better at relative changes.
That seems to be the hypothesis. So if we connect this back to the bigger picture for an engineer choosing a method, this comparison is super insightful. The best method isn't universal. It really depends on your specific equipment and knowing its limitations.
Right. If you suspect your SA's absolute calibration isn't perfect.
Then the direct method, despite its conceptual simplicity, becomes inherently less trustworthy. The power doubling method, by cleverly relying on relative changes, becomes a much more robust and reliable choice in that common scenario because it sidesteps the SA's absolute calibration weaknesses. And Y factor, of course, remains the preferred choice if you have the dedicated, calibrated noise source available, as it's designed to minimize many of these errors systemically.
Got it. Any final caveats on the comparison?
Just one reminder from the source that applies to all these measurements they presented. Remember that coaxial to waveguide transition? Its losses were included as part of the DUT's measured RET.
Right, they didn't subtract it out.
Correct. So the actual S of the ME amplifier itself might be slightly lower than the numbers reported across all three methods.
Yeah.
It's a small detail, but another layer of real-world measurement complexity knowing exactly what's included in your DUT definition. Hashtag, tag, outro.
So after that incredibly detailed exploration, what does this all mean for us? We've taken this deep dive into noise factor measurement, and it's clear it's a multifaceted challenge, isn't it? A real pursuit of precision. We've seen various techniques, each demanding really careful attention to detail and a solid grasp of the principles involved.
Definitely not just plug and play.
Not at all. The power doubling method really stood out, I think, as a strong contender, especially if you're dealing with devices that have a higher noise factor, or maybe you just don't have that specialized noise generator handy. Its independence from the spectrum analyzer's absolute accuracy makes it seem really robust and, frankly, quite practical for many labs.
Yeah, it has some compelling advantages in typical lab settings.
Then there was the direct method. Conceptually simple, yes, but wow, it really hinges on the absolute accuracy of your SA and getting that gain measurement spot on. We saw how that could be its Achilles heel, particularly at certain frequencies where maybe the SA's calibration isn't quite as reliable.
That reliance is its major trade-off.
And of course, the Y-factor method. It remains the benchmark, the common and effective approach, if you have the right gear, especially that calibrated noise generator. It's designed to systematically minimize many errors.
Indeed. And this whole journey through these methods, I think it really underscores that getting a precise number for noise factor, particularly at these higher frequencies like 24 to 33 gigahertz we talked about, it's just far from trivial.
Yeah.
It's so much more than just plugging numbers into a formula. It's about really understanding the subtleties of your instruments, knowing their strengths and weaknesses. It's about the physics of noise itself and about meticulously anticipating all those potential pitfalls in your setup, the temperature drift, the mismatch ripples, and especially that crucial difference between accounting for input versus output cable losses.
That cable loss point feels like a recurring theme.
Because it's such a common error. And these choices, they aren't just academic. They directly impact the validity of your results, which in turn influences design decisions, component selection, and ultimately the real-world performance of the electronic devices we all rely on.
Absolutely. So ultimately, knowing these different methods, understanding their pros and cons, their dependencies, it really empowers engineers, doesn't it?
Yeah.
It lets them make informed comparisons, choose the best components for their specific needs, and importantly, debug results that just seem off.
That debugging aspect is crucial.
So maybe the final thought for you, our listener, the next time you see a reported noise factor for some RF component, and maybe it looks astonishingly good, almost too good to be true.
Yeah.
Our deep dive today suggests your very first skeptical question should probably be, Okay, how exactly did they measure this? And specifically, did they correctly account for the losses in their output measurement cables?
Aha, back to the cables.
It's such a subtle point, but as the source showed so clearly, it can make all the difference between an accurate, trustworthy measurement and one that's just overly optimistic, potentially misleading you down the wrong design path.
It really can.
So the next time you marvel at the range of your Wi-Fi, or the speed of your data connection, or the clarity of a satellite signal, maybe take a second to remember that invisible battle against noise being constantly waged deep inside the electronics. It's a fight measured in fractions of a dB, but it makes all the difference. What stands out to you from today's exploration? What overlooked detail might you be more vigilant about now?